When radiation interacts with matter, it displays particle-like properties. When this radiation is passed through a prism and then obtained on a photographic plate, you obtain emission spectrum. So dark lines appear exactly at the same position where the lines in the emission spectra appeared. When radiation are propagating or when radiation is moving, you can say that it exhibits wave-like properties. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. So today we are back with session 4 of your chapter Structure of Atom. So in last class, we discussed about the developments leading to Bohr model of atom. Yes. And then we discussed about electromagnetic spectrum and the characteristics of electromagnetic waves. Then we discussed about the particle nature of matter, where we studied about the Planck's quantum theory, which was able to explain the two effects that we studied, photoelectric effect and the black body radiation. These two phenomena also we discussed, right, in last session. So in today's session, we'll be discussing on atomic spectra, which was the second development which led to the discovery of Bohr model of atom, right? Yes. And then line spectra and line spectrum of hydrogen, which is very important. And finally, the Bohr's model of atom. Yes. So in last session, we discussed about the first development which was leading to the Bohr model of atom, that was dual nature of electromagnetic radiation. So we discussed or we understood that the electromagnetic radiation is having particle as well as wave nature. So from this, what can you conclude? Is it only particle nature, or is it only wave nature, or is it both? Or in which circumstances or in which conditions it acts as particle or it acts as waves? So as you can see here, when radiation interacts with matter, it displays particle-like properties. So when does your electromagnetic radiation act as particle? When it comes or when it interacts with matter. Yes, now when radiation propagates, it exhibits wave-like properties. Yes, in the examples of interference and diffraction can be taken in this case, right? So when radiation are propagating or when radiation is moving, you can say that it exhibits wave-like properties. So I hope it is clear that electromagnetic radiation behaves as particle as well as wave. So this is clear. Now moving on to the second development which was leading to the Bohr model of atom, that is atomic spectra. Yes, so the word spectrum or spectra might be a little bit familiar for you. Yes, so let us see. When a white light is passed through a prism, the wave with shorter wavelength bends more than with a longer wavelength. So what exactly is happening in atomic spectra, or how do you obtain a spectrum? Yes, when white light is passed through a prism, you know that you obtain these 7 colors, that is Vidhyaashram, right? So your white light consists of Vidhyaashram. This is already a known fact for you, right? So when we pass white light through prism, it splits into the Vidhyaashram. So as you can see here, the shorter wavelength one bends more than the longer wavelength one. So as you can see here, when white light is passed through the prism, it splits into the 7 different colors, and the red one is the least deviated because it is having the highest wavelength. Yes. So highest wavelength means red color will be having the lowest frequency, right? Yes. So the red color will be the deviated the least, right? And the last one, that is violet, it will be having the wavelength which is least. That means frequency is the highest and it is deviated the most, right? So that is what is written here. The red color having longest wavelength is deviated the least. So that is why it is on the top, right? It is deviated the least. And as you can see, the violet color is deviated the most, right? So violet light having the shortest wavelength is deviated the most. So what are you able to observe here? Yes, there is a continuous spectrum that is obtained when you pass white light through a prism. Yes, we understood that when we pass white light through a prism, we obtain the Vidhyaashram. Yes, and the Vidhyaashram or the spectrum that we obtain is a continuous spectrum. See, you obtain a spectrum like this. Each color merges onto the upcoming or the next color. You obtain a continuous spectrum wherein which there will be no separation. See, as the violet ends, the indigo starts, right? You are not able to see any separation between these colors. There, a continuous spectrum is obtained. Yes, so this is what is continuous spectrum. When white light is passed through prism, it splits into 7 different colors, red to violet, and these colors are continuous, that each of them merges into the next. Right? As you can see, there are no different separations, or you can't say that the violet ends here and the indigo starts here. Right? It is a continuous spectrum that is obtained. Clear? Now moving on to the next type of spectrum, that is emission spectrum. Now what is emission spectrum? When radiation emitted from a source are passed through a prism and then received on a photographic plate, you obtain emission spectrum. So what does this sentence mean? Let us try to understand. Okay, so let's take an example of any atom. So it is easy to consider hydrogen atom. So let's consider that. We know that there is a positively charged nucleus, right? Okay. So in the case of hydrogen atom, we know that only one electron is present, and it is present in this shell, let us say. Right. Yes. So only one electron is present. So what happens is the electron absorbs the energy which is given onto the atom and it moves to excited energy states. What happens is from this energy state, it moves to the higher energy states. So these higher levels or higher energy states are called as excited states. Right. And from the energy level from which it has jumped to higher energy level, that is this one, it is called as the ground state. Okay. So what can you say? When energy is supplied to the hydrogen atom, the electron accepts this energy. Yes, now the electron is having some energy with it. No. So it gets excited and it moves to the higher energy level or the excited states. Now what you have to understand is, in the excited state, it is unstable. Yes, the electrons can't stay in the excited state for a long time. It is an unstable state. So what happens? The electron from the excited state, it will come back to the initial state or the ground state. So let us say the electron from this energy level absorbed energy and moved to this higher energy state. So as I said, it is unstable. So the electron can't remain in the excited state for a long period of time. So it comes back to the ground state. Right. So when from a higher energy level, the electron is coming to the lower energy level, it emits radiations. Clear? It emits radiations. So when this radiations is passed through a prism and then obtained on a photographic plate, you obtain emission spectrum. Clear? Yes. So this emission spectrum is, as you can see here, it will be obtained on a photographic plate. That will be a black background on which you will obtain the colored lines you can see here. So these lines, these colored lines that you can see corresponds to the wavelength which has emitted radiations, right? This corresponds to the wavelength in which the radiations are being emitted. Clear? So the black background wherein which you get the colored lines are the wavelengths which has emitted radiation. So this is about emission spectrum. Clear? So now about absorption spectrum. So you can basically say that absorption spectrum is the opposite of emission spectrum. So what does that mean? From the name itself you can say absorption spectrum. So it is basically the wavelengths in which or the spectral lines that you obtain in those areas where the radiations are being absorbed, right? So when light is passed through vapors of a substance and transmitted light is then allowed to strike a prism, dark lines appear on the continuous spectrum. The dark line indicates the radiation that are being absorbed. So dark lines appear exactly at the same position where the lines in the emission spectra appeared. Clear? So this is what I was telling. It is kind of exactly opposite to the emission spectrum. So as you can see, this is emission spectrum we studied. Now this diagram that you can see, this is the absorption spectrum. Clear? We have studied about continuous spectrum, right? So on a continuous spectrum band, you will be able to observe this dark lines. See, you can see black lines there, right? So these are the wavelengths in which the radiations are being absorbed. So as you can see, the line is here and in the emission spectrum, the line is here. So exactly on the same position, the lines will be observed. So basically you can say that these are opposite to each other, right? So in an absorption spectrum, on a continuous spectrum, dark lines are observed. So this is about continuous spectrum, emission spectrum and absorption spectrum. Clear? So in emission and absorption spectrum, as you can see, lines appear on the photographic plate, right? So these lines, what is the importance of this lines or line spectrum? So let us see, the emission spectrum of atoms in the gas phase only emits light in specific wavelengths with dark spaces between them. We observed this in absorption and emission spectrum, right? So what exactly is the importance of this line spectra that we observed in emission and absorption spectra? So as you can see, every element has unique line emission spectra and many elements were discovered using line emission spectra. So that is actually the importance of line spectra. Yes, so many elements were discovered using the line spectrum of those particular elements, and each of the elements are having a unique line spectra. Clear? So in detail, we are going to study about the line spectrum of hydrogen, which is very, very important. Okay, so hydrogen, as it is the simplest element which is consisting of only one electron, it is easy to understand the line spectrum of hydrogen. So we'll be going to discuss about it. So how exactly do you obtain the line spectrum of hydrogen? Yes, let's begin with that. So as you can see here, there is a gas discharge tube. There is a discharge tube. Yes, there will be an anode and cathode. Under low pressure and high voltage, there a gas will be present. Okay, so when high voltage is passed through it, what happens? Energy is given to the hydrogen gas. So inside this discharge tube, hydrogen gas is present. Yes, so when we discussed about emission spectra, what did we discuss? When the electron gets energy, it jumps to higher energy state, right? So when inside this discharge tube, when a high voltage is supplied to the gas, what happens? Energy is obtained by the electrons, right? The atom gets energy, or your hydrogen gas absorbs energy. What happens? As you know, there will be a nucleus and there are different shells present, right? So what happens? The electron absorbs energy and moves to higher energy states, the excited states. As said, the excited states are unstable, so the electrons comes back to the ground state. So when coming back, what did we study? It emits radiations, right? So this emitted light is then passed through a prism. See, from excited state, when it comes to the lower or ground state, what happens? The radiation or the light which is emitted is passed through the prism. Right, and then as we know that when it passes through the prism, it deviates, and that is obtained on a photographic plate. The lines which is coming out of the prism is obtained on a photographic plate. Yes, so the beauty of the line spectrum of hydrogen is that you obtain different series of lines. Clear? So what is this different series of lines? Let us understand. So basically you are going to study about 5 different series of line spectrum of hydrogen, which are named under the scientists who discovered them. So as you can see, Lyman series, Balmer series, Paschkin series, Brackett series and Fund series. The P is silent here, it is Fund series. So what is about this? Different series of lines or different spectral lines that you can observe. So as said, from the higher energy levels, when it comes to when the electron moves back or jumps back to the lower energy levels, it emits radiations which is caught on this photographic plate. So that will be observed as a set of different series of lines. So let us say in a photographic plate, we obtain this radiations. What happens? Here you can see a set of lines. Again here a series of lines. Again here a series of lines. So that is basically what I have shown here. So how exactly it is obtained? Let us see. So the same diagram we can use. There is a positively charged nucleus and there are different shells present. So first let us discuss about the Lyman series, how Lyman series is obtained. Okay. Yes. So there is a nucleus. There are different shells present. Okay. Let us consider this. Okay, now there is an electron here, it jumped to this energy level. Now the electron is coming back to the ground state. So let's say the first one is n is equal to 1, the first energy state. This is 2, this is 3 and this is 4. Okay, so there is a possibility that the electron can jump from the fourth energy state to the first one. Right. Yes. Now let's say from the fourth energy state, the electron is moving to third and then coming back to 1. That is also possible, right? So it can come from third to 1, right? It can also come from 2 to 1, right? So in this way, electrons can jump from each of the higher excited states to the ground state. So what you have to understand is, from all the higher energy states, the electron is finally coming to the first energy state or the ground state, right? So those series that are obtained from any higher, when the electron jumps from any higher energy state to the first energy state, which is n is equal to 1, comes under the Lyman series. So as you can see here, from n is equal to infinity, the highest energy state, it is coming to, or the electron is jumping back to the first energy level, right? From 7 it is coming to 1, 6 to 1, 5 to 1, 4 to 1, yes? So from whichever higher energy state, finally when it is falling back to the first energy level, the series of line that is obtained comes under the Lyman series. Okay, so this corresponds to, or this comes under the ultraviolet region. Okay, so that is also important. Now next, moving on to Balmer series. Yes, so as you can see here, it corresponds to n is equal to 2. That means in the same diagram as you can see, from any higher energy level, I have only drawn till 4, there can be 5, 6, 7 till infinity, right? So from any higher energy level, when the electron falls back to n is equal to 2, from here it can fall back to 2, from higher energy states it can fall back to 2, right? Yes, so from whichever higher energy state it falls back to 2, the series of lines that are obtained comes under Balmer series. Yes, that comes under the visible region. Okay, so Lyman series comes under ultraviolet and Balmer series is visible region. Okay, now moving on to Paschkin, as explained in Lyman and Balmer, from any higher energy state, it moves or it jumps back to the n is equal to 3, the third energy state. Clear? So for Paschkin, it comes under the infrared region. So what you have to remember is, Lyman is UV, Balmer visible, and Paschkin, bracket and Pfund comes under infrared region. Clear? Now coming to bracket series, from any higher energy level, it moves back or it jumps back, the electron when it jumps back to n is equal to 4, the fourth energy state. Yes, the series obtained comes under bracket series. Now for Pfund, the same way, from any higher energy state coming back to n is equal to 5. So the series of lines, so from any level when it is falling back to n is equal to 1, the first energy state or the ground state, the corresponding, see, many lines will be obtained. Like this group of lines is called as Lyman series, Balmer, Paschkin, bracket and Pfund. Clear? So I hope the line spectrum of hydrogen is clear. The diagram that is shown here, it is clear for you. Now moving on to, yes, Lyman series, n1 is equal to 1 and n2 is equal to 2, 3, 4, etc. So that means finally where it is coming back to, it is 1, right? Yes, and from any higher energy state, it can fall back to 1. So that corresponds to n2 is equal to 2, 3, 4, 5. Any value can come up. Yes, and falls under UV region. Balmer series, n1 is equal to 2, falls back to 2, and from any higher energy state comes under visible region. Now Paschkin series, n1 is equal to 3, n2 can be 4, 5, 6, etc. It comes under IR region. Bracket series, n1 is equal to 4 and n2 is 5, 6, 7, etc. comes under IR region. And Pfund series, n1 is equal to 5 and n2 can be 6, 7, 8, any values. IR comes under infrared region. So I hope it is clear. Now to calculate the wavelength associated with each of the spectral lines, Rydberg formulated an equation from which you can calculate the wavelength of each of the spectral lines. Right. So Rydberg in 1890 gave an expression for the calculation of wavelength of spectral lines in different series of hydrogen spectra. So we have studied about the hydrogen spectra, the line spectrum of hydrogen. So each of this series corresponds to some wavelength, right? So what we studied about emission spectrum or absorption spectrum or whichever spectrum we studied, in certain wavelengths this is happening. So we studied about the line spectrum, but it corresponds to which wavelength exactly. So for calculating that, Rydberg formulated this equation as you can see here. Nu bar, what is nu bar? It is wave number, right? So nu bar is equal to RH into 1 by n1 square minus 1 by n2 square. Clear? So nu bar is wave number which is equal to 1 by lambda, right? Nu bar is equal to 1 by lambda. We already know that. So from here, once you calculate this value, if you take the inverse, you will obtain the value for wavelength, right? So nu bar is equal to RH into 1 by n1 square minus 1 by n2 square. So what is RH? RH is Rydberg's constant having a value 109677 centimeter inverse. Clear? So what is this n1 and n2 corresponding to? So just this slide we saw that, see, in Lyman series n1 will be 1. Clear? So if we are talking about Lyman series, if you have to calculate the wavelength associated with Lyman series, n1 should be 1. So what about n2? It can be 2, 3, 4, etc. Any value, right? So from which energy state it is falling to n is equal to 1, that corresponding value you have to substitute in n2. Clear? Yes. So let's do a problem based on this. What is the maximum number of spectral lines that can be observed when the excited electron of hydrogen atom in n is equal to 6 drops to the ground state? So from n is equal to 6, yes, from where it is falling, the higher energy state is given, n is equal to 6 to the ground state. So it is falling back to n is equal to 1. How many spectral lines are obtained? That is what we have to calculate. So let's see. Okay, so this corresponds to n is equal to 6, n is equal to 5, n is equal to 4, n is equal to 3, n is equal to 2 and n is equal to 1. So from the question, you know that from n is equal to 6, it is falling back to 1. Alright, so it can fall back to 1. Electron is falling back to 1. Okay, now it can fall back from 5 as well, right? From 6, it is going to 5 first. And from 5, it is coming back to 1. That is also possible. Yes, from 6, it is coming to 4, then coming to 1. That is also possible. Right. So basically, you can obtain a set of series like this. So is this the only possible thing? So what I am trying to say is from n is equal to 6, it can come to 5, then come to 4, then come to 3, then to 2, then to 1. That is also possible. So I can say that it can come from 6 to 5, right? 6 to 4, 6 to 3, 6 to 2 and 6 to 1. Okay, so 6 to 5. Now from 5, it's another possibility that are there. From 5, it can come to 4, 3, 2 and 1, right? So from 5 to 4, 5 to 3, 5 to 2 and 5 to 1, right? Now same way from 4 to 3, 4 to 2, 4 to 1. Yes, 3 to 2 and 3 to 1. Finally, 2 to 1 is also possible. Right? These many spectral lines are possible when the electron is falling back from n is equal to 6 to n is equal to 1. So, as you can see, you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 spectral lines can be obtained. Clear? So, this is kind of easy to calculate, but in all the cases, the number of spectral lines can't be calculated in this form. You can't count it. So, the general formula that you can use is n into n minus 1 by 2. So, n corresponds to from which energy state the electron is falling back. So, if you are taking the question into this equation, n is equal to 6 we know. So, what it will be? 6 into 6 minus 1 by 2, that is 6 into 5 by 2, that is 30 by 2. Which will give you 15. Yes, 15 spectral lines. So, this equation also you can use in these types of equations. So, I hope the line spectrum of hydrogen is clear. Yes, now moving on to the Bohr's model of atom. So, till now we discussed about the developments which we are reading to the Bohr's model of atom, right? So, from these experiments or these developments that we studied, that is dual nature of electromagnetic radiation and atomic spectra, Bohr was able to formulate his Bohr's model of atom. Yes, so Niels Bohr in 1913 proposed a new model of atom on basis of Planck's quantum theory. So, we will study about the postulates. So, what exactly is Bohr's model of atom? We are going to see. So in an atom, the electrons revolve around the nucleus in certain definite circular paths called as orbits, right? There will be a nucleus and there are different circular paths you can see in which the electrons are revolving around the nucleus, and the name of each of these energy states are called as orbits. Right, this was the first one, and each orbit is associated with definite energy, and therefore these are known as energy levels or energy shells, and these are numbered as 1, 2, 3 or KLM. So as you can see, there are different orbits in which electrons are revolving around the nucleus. So each of these orbits, you can see this orbit, this orbit, this orbit, each of the circular paths has a definite energy. Yes. That is what is written here. Each orbit is associated with a definite energy. Each of these energy levels are having a corresponding energy. Hence, you can also call it as energy levels or energy shells. And it is represented by 1, 2, 3, or else you can also represent it as KLM like that. KLMN. You can represent it like that. Or 1, 2, 3, 4, 5, 6 like that. You can represent the each orbit or each energy levels or each energy shells. Clear? Now, as long as electron is present in a particular orbit, it neither absorbs nor loses energy, and its energy therefore remains constant. So, as discussed, there are different shells present. Yes, when the electron, let's say only one electron is present, when the electron is present in that particular orbit or that particular energy level, there is no absorption or release or emission of energy that is taking place, right? As long as the electron is present in that particular energy level, there will be no emission or absorption of energy. But when it moves from one energy level to higher energy level, or when it moves back from higher energy level to lower energy level, there will be a change in energy, or there will be an emission or absorption taking place. That means a change in energy will take place. So as long as it is present in one particular orbit, it is not moving anywhere, no energy change will take place and the energy will remain a constant therefore. Clear? Now, the frequency of radiation absorbed or emitted when transition occurs between two stationary states that differ in energy is given by this equation. Yes, so as I said, when it is present in one particular orbit, no change is happening. But when it is moving from, let us say, the electron absorbs energy and it is moving to higher energy state. So what is happening? Energy is being absorbed there, right? And when from the final energy state, it is coming back to the ground state. Excited state, it is coming back, it emits radiations, right? So there is basically a change in energy that is taking place, right? So the change in energy is represented by delta E and associated when the associated frequency, as you can see here, when it is coming down to the ground state, radiations are emitted. So the frequency associated with it can be calculated by the equation nu is equal to delta E by H. So what is this delta E? It is the difference between these energy levels, right? So you can also write it as delta E by H. You can also write it as E2 minus E1 by H, right? So E2 is the final state in which the electron has reached and E1 is initially from where it has jumped. Clear? So that is delta E by H, which will give you the frequency associated with the radiation that is being emitted or absorbed. Clear? Now, the angular momentum of an electron in a given stationary state can be expressed using this equation. So, what you have to understand is, these orbits, the electrons can't revolve around any orbit that is possible. So, the orbits in which the electrons will revolve is basically those orbits whose angular momentum is an integral multiple of h by 2 pi. So, that is the equation that is given. Angular momentum, you know that it is mvr. So, E is written as subscript here, that it's mass of electron, velocity and the radius. So, angular momentum must be an integral multiple of h by 2 pi. So, you can write it as mvr is equal to nh by 2 pi. So, this n value must be an integer. So, what is that you have to conclude or understand from the statement is that any orbital, electron can't revolve around the nucleus in any orbital that is possible. The angular momentum of this orbital must be an integral multiple of nh by 2 pi, or it must be an integral multiple of h by 2 pi. Clear? The n value can be 1, 2, 3, etc. Integer values. Clear? Now, when energy is supplied to an electron, it absorbs energy only in fixed amounts and jumps to higher energy state. The excited state is unstable and electron may jump back to lower energy state. This we have already discussed till now. Clear? So, I hope the postulates that was formulated or postulates which were given by Bohr's model of atom is clear for you. So, in the next session, we will be studying about the Bohr's theory of hydrogen atom in detail, in which we will be studying about the various equations for finding out the energy, radius, etc. of different orbits. In detail, we will be studying about certain equations which is of importance for your examination. Clear? So, in the next session, we will be studying about that, and then line spectrum of hydrogen. So, line spectrum of hydrogen we have already studied, right? So, how exactly using the Bohr's theory for hydrogen atom, we will be able to explain the line spectrum of hydrogen. We will be studying, and then towards the quantum mechanical model, which were the developments which eventually led to the quantum mechanical model of atom, even that we'll be discussing in the next session. So, what and all we have discussed in this session is clear for you. I hope that it is clear for you. So, that's all for today. Thank you.